Actually, a group is an algebraic structure. So what we wish to do first is to introduce ourselves to what we mean by an algebraic structure, and then extend now to what a group is. And we say that a set, of course, we've talked about sets and we understand exactly what sets are. And we call them mathematical objects, and in this case could be elements, you see, the ones that we've been talking about. Equipped with one or more, look at this, one or more, you see, one or more binary operations, you see, one or more than one binary operation. And the beauty is that we've talked about binary operations. We know exactly what binary operations are. This is something that you can always go back to at any given time. And if anything, we've done a lot in operations, and I knew why. It is because there are quite a number of instances that we shall use. And here is one instance that we use, and that is groups. And we say that if we equip a set with a binary operation, then that set becomes an algebraic structure. And in this case, we call that set maybe G. With a binary operation, let's denote that binary, because we don't know what that binary operation is at this point in time, we call it asterisk. And therefore, if we equip that, so that we have this, look at how we write that. Look at this. That is how we write. If we equip this set G with that is this binary operation asterisk, then we call this an algebraic structure. And we told that now we talk about the different properties of the algebraic structures. Of course, you see these are properties that you've come across a number of times in a number of concepts. We have what we call associativity, what we call the associative law. And here, you see when we talk about associativity, we're talking about three properties, where if we subject those properties to that binary operation, then it doesn't matter which ones start. You can see A, this operation B, asterisk C, is no different from, you see here we've started with A and B. It's no different from having this and C, and then again, and then now asterisk A. And we're given examples of algebraic structures that are associative. Here we talk about a set of natural numbers. The binary operation here is addition. Here the set of natural numbers. The binary operation here is multiplication. This one is the set of rational numbers. The binary operation is addition. The set of rationals equipped with multiplication. The set of real numbers equipped with addition. The set of real numbers equipped with multiplication. We're told that all these are associative algebraic structures. And for us maybe to have a better understanding, look at what I'm talking about here. Look at, okay, let me enlarge this where it's, oh yeah, see here? Kindly allow me to use this. Just to go, let's pick, let's say the set of natural numbers. You see, we're told that this one is an associative. You see, look at this. Equipped with the, you see, we told that this is associative. Why is it the case? It obeys the associativity law because natural numbers, let's say 2 plus 3 plus, let's say 7, is this one is no different from 2 plus 3 plus 7. You see? Are you saying that? You see, we have this. So this will give us 12, and the same. This one also will give us 12. So it doesn't matter which ones we start. You can see the first two started here and then added to this. It's no different from maybe having the last two added together and then adding to this. So that is what we mean by associativity property, right? So that is important. And you can see when we're talking about again multiplication, look at if we're talking about multiplication, you can see again if we have multiplication here, multiplication here instead of plus. So meaning therefore we have that dot. That dot represents multiplication. So we could have 2.3, of course, by 7 is no different from 2.3 by 7. And I think you can see that will still give us, this one gives us 42, and this one also will still give us 42. So you see that the set of natural numbers, and of course, if we have this, then we're talking about the set of natural numbers equipped with multiplication, you see. So here, this one is also associative. That is what we mean when we're talking about exactly what is being said here. And we're told that an algebraic structure is said to have an identity element. So we have another element that is special here. Of course, this one is we're saying that it is associative. That is associativity. Now, when we talk about existence of an identity element is an element that will leave another element unchanged when you combine the two elements using the binary operation. Like just to go back to this document here, when we're talking about the set of natural numbers, we have in the set of natural numbers, we have one number when you multiply, or when you multiply by any other natural number, you'll always have. So we're talking about this multiplication. You'll always have that number. Which number is that? In the set of natural numbers, we have, you see, there is 1, 2, 3, and that continues. And we have one element. There is an element in the set of natural numbers, right? There is an element in the set of natural numbers such that let's call this number E, such that E multiplied by 1, or 1 multiplied by E, whichever that starts, is always equal to, no, not 1, sorry. What am I talking about here? I think I'm overthinking there. I've moved too fast. If anything, I'm giving you what we should just relax. This E multiplied by, let's say, X, is no different from X multiplied by E, and it will always give you X. Which number is this in the set of natural numbers? That when you multiply, of course, we're saying here for every X in the set of natural numbers. Which number is this that when you multiply by any other natural number, you'll always have that natural number? Yes?
0.
0.
Wow.
We have a 0 here. When you multiply, look at it. When you multiply a 0 by any of these, it will leave 2 the same. It will leave 3 the same. Unchanged. A nice try, but not correct. Yes? Another fellow to try? Yes?
1.
1, yeah, that is it. So 1 in this case is what you call the multiplicative identity. That is exactly this one. Now you notice that this E in as far as the set of natural numbers, E is actually 1, you see, and this one is what you call multiplicative identity. In fact, it is the identity element. But now you see, because this entails the operation, the binary operation that is in force here is a multiplication. That is why we call it multiplicative identity. Now look at another one. Let me give you another one. Maybe let's see that. So for purposes of making us understand that, because you see this will be very important. Look at this. How about the set of integers? In the set of integers to the left, we have, of course, -3, -2, -1, 0, 1, 2, and that continues 3, and that continues. Now, which one is, what is E here? In as far as this, maybe let's talk about this structure, plus. Does the set of, does this structure, algebraic structure, does it have, or does the set of integers have an additive identity? Which number do we, which number do we have as a number that whenever you add to any other integer, you'll always have the same integer? Yes? Somebody tell us. in as far as addition is concerned, our E is equal to, because since 0 plus x is equal to x plus 0, which is equal to x for every x in the set of integers. You see? That whenever you add, please kindly mute. Whenever you add any integer to 0, you'll always have that integer. And therefore, we see that this one is what you call additive. You see? This one is an additive identity. Right? That is what you call an additive identity. So you can see that is what we mean by identity element. With respect to binary operation, this one is the general binary operation we're using asterisk. If for every member of that G, then there exists an element E such that A, that operation E, or it doesn't matter whichever starts, it's always A. It means that it fixes, you see, this E fixes elements of A. It doesn't change. And as you can see in the set of natural numbers, when you're talking about multiplication, our E is 1, because A multiplied by 1, which is the same as 1 multiplied by A, is equal to A. Now, in the set of integers, the additive identity E is 0. A plus, you see, we shall have A plus 0 is no different from 0 plus A, which is equal to A. And again, we go ahead and we told you that an algebraic structure may or may not have an identity element. So it is not a must that it is. And look at this. You see, when you look at this, this is the set of natural numbers equipped with plus. You notice that it doesn't have an identity element. And it is good that one of you mentioned the 0, and you can see that 0 is not in the set of natural numbers. You see? And that is why I was hesitant when we were talking about this. Somebody said 0, but now 0 is not inside here. So the set of natural numbers doesn't have 0, the additive that is identity, but it has what you call multiplicative identity. You see? So we say groups, rings, and fields are examples of various algebraic structures we come across in algebra, and the ones that are of interest in as far as our unit is concerned are these two, a group and a ring. Now, let's now define what a group is, and here it is. And the definition, and I think I mentioned this last time, and I say that don't ever joke with definitions. You will be expected to define terms in campus mathematics. So if you're asked to, for example, if you're asked to define a group, you should be able to define a group as it is required. And in looking at this, you notice that it has 4 properties. Without talking about these 4 properties, that which you will have defined as a group is not a group. What I'll only do is to condense these G3 and G4 so that you don't have to, just in case, I'm saying just in case, it's not really a guarantee that you're gonna see this. But what I'm saying is that just in case you come across, then you notice that this one, like this one here, this one is condensed into 1. So, and therefore there is no need to talk about right or left identity element. In this case also, the existence of inverses, then you don't have to talk about right and left inverse. And for your information, I think this is something that we must have a clear idea of what is. In fact, even before defining what groups are. And this is what I wish to mention. And kindly please look at this. I wish to have us look at this. You see, we've talked about the set of integers equipped with addition. Yes, and we've seen that it has what you call an additive identity 0. Now, this additive identity 0 is very important whenever we're looking for what we call inverses of those of the members of the set of integers. Are you getting that? So let me mention something small here, even before defining what groups are, and please be very keen. Now, when we have, of course, members of Z, somebody give us any member of Z. Any one of us, please. Any integer, kindly, please. Identify any integer.
That's
-1.
Yes, somebody has talked about -1. Another one is 30. right? And for those two guys who've contributed, say hi to each other. Ah, say hi. Unmute and say hi. Okay.
Hi.
Perfect. I'm not getting the other response. Huh?
Hi.
Wow, that is nice. You know, that is okay. Yeah. Kudos for participating in that. We've talked about -1 and 30. Those ones are integers. They're members of the set of integers. Now, note something here. As we've said, that 0, which is also in Z, this one is what we call an additive identity. And this identity element is a crucial one. Whenever we're looking for the additive inverse of -1, an additive inverse, we have what we call the inverse of -1 and the inverse of 30. Now, the inverse of -1 is that number which is also in the set of integers, which is also an integer, that when you add -1 to, you'll always get an additive identity. Which number is that?
One.
Perfect. Therefore, implying that 1 is the additive, you see, that is the additive inverse of -1. Now, what is the additive inverse of 30? That number, when you add to 30, you will get the additive identity. Yes? It is -30. Come on, 30 plus -30 is 0, right? The additive, that is, yes, the additive inverse of 30 is -30, because when you have 30 plus -30, you're going to get 0, which is the additive identity. This additive identity is unique. Let me tell you that. Kindly please know that. The additive identity is unique. This one is unique. This one. So it's important that you know that. Now let's go to our definition now. At least you know what that is. Now, a group is it has to be a non-empty set. G and a binary operation, you can see this. This one is a general. It could be plus, it could be multiplication, it could be addition, it could be multiplication, and at times we use this. If the following 4 axioms are satisfied. So if you find a non-empty set equipped with a certain operation that does not satisfy these 4 properties, that is not a group. And when we talk about the first property, we have what we call closure property. Closure property is very simple. That it states that whenever you pick any 2 members of that non-empty set and you add them, or you subject that binary operation, like in this case, it could be plus, it could be multiplication, or any other operation, binary operation that is, then you're going to have an answer that is also a member of an element that is also a member of that key. That is what we mean by closure property. Just to give you an idea, in this case, the closure property satisfied with respect to the set of integers under addition is that whenever you have A plus B, this one is always an integer for every 2 integers. And I think you know that whenever you pick any 2 integers and you add them, you notice that the answer is always another integer. And therefore, we say that the set of integers is closed under addition. The same case also, whenever you multiply any 2 integers, you use a dot, of course, for multiplication. Whenever you multiply any 2 integers, you're going to always have another integer. And therefore, the set of integers also is closed under multiplication. Now, when we look at the next one, we're talking about associative property. And I've talked about this, that if you have 3 elements that belong to that set G, and it happens that you subjected that binary operation, it doesn't matter which ones start. whichever way that you carry out that operation, you'll always have the same one and the same solution. And that is why you see, if you start with these first two, and then next that one, or you start with the last two, then followed by the first one, you're going to have the same result as this. And that is what you call associativity. In the case of existence of identity element, in fact, I'd suggest all this is not necessary. That this property concerns the existence of the identity element. And what we have in this case is that there exists, and that is an element E called, you see, an identity element, of course, that is an identity element, such that, you see, such that, look at this. So you condense all this instead of all this, such that that is asterisk E is equal to E asterisk A is equal to A for every A in G. Somebody, there could be someone who wants to, okay, I can see some fellows want to join. Okay. So you see that. So instead of all this, you can see we are combining this is equal to this and all this. This one is equal to this, and this one is equal to A for every member of G. Like in the case where we talked about with respect to the set of natural numbers, we noticed that the set of natural numbers does not have an identity element under addition. But under multiplication, it has an identity element. And the identity element in that case is 1. 1 multiplied by any natural number is, or rather, any natural number multiplied by, you see, we're saying here now, let's say any natural number multiplied by 1 is no different from that 1 multiplied by any natural number, which is equal to A for every natural number. And we notice, therefore, that the set of natural numbers equipped with the binary operation multiplication satisfies G3. If anything, it satisfies G1, it satisfies G2. Yes, you see, anytime you multiply any two natural numbers, you'll always have another natural number. That is closure. When you come across, when you bring in any three elements of the set of natural numbers, it doesn't matter which ones start, you still have the same multiplied. The existence of that is a multiplicative identity, yes. The set of natural numbers as 1 as the identity that is in the set of natural numbers, you see, such that whenever you multiply any natural number by 1, whichever way you start, whether you start with a natural number followed by, you see, the identity, or the identity followed by the natural number, you're going to always have that same natural number. And therefore, it satisfies that. The fourth one is the existence of what you call right and left inverse. Also, in this case, it doesn't matter. What we do in this case is that we simply say that for every element in G, there exists. And this is where the big issue is. In fact, I would want to ask you, does the set of natural numbers equipped with multiplication satisfy this property 4? I would say no. Why? You see, the set of natural numbers consists of 1, 2, 3, and so on. Now, let's talk about 2. Of course, 1 multiplied by 1 is 1. Remember, I say that when we're talking about inverses, what you're supposed to have in mind is what you call the identity element. And with respect to the set of natural numbers, equipped with multiplication, the multiplicative identity is 1. So when we're looking for the inverses, we're looking for those numbers. When we multiply by any natural number that we pick, it must give us the identity element 1. And what we see in this case is that if we pick 2, what is it that you can multiply by 2 in order to get 1? Yes? Any one of us?
Half.
Perfectly put. Thank you very much. Correct. Now, is a half a natural number? Yes. Is a half a natural number? I need an answer. Come on. A. No, not necessarily the one who responded. You see, look at this. We have the set of natural numbers equipped with multiplication. Of course, one is the multiplicative identity, as we said earlier.
No.
Thank you. It is not, since you see 1 multiplied by A is no different from A multiplied by 1, which is equal to A for every natural number. In simple terms, 1 fixes A, if we engage multiplication, fixes every natural number. Now, when we talk about inverse, you see, let A, you see, let A be a natural number. Then, for us to get, you see, 1, A inverse, which is the same as 1 over A, is its inverse. E.g., you see, for us to get 2, you see the inverse, e.g. the inverse, let's have that, look at that, the inverse of 2, look at this, the inverse of 2, no, yes, the inverse of 2 is a half, which is the same as 2 raised to the power negative 1. So that, look at this, you see, it is the inverse, because what we need is we need to have a number that when you multiply by 2, no, let me use the symbol here, not multiplication, not this multiplication. Let's use the dot, because that is exactly what we're using there. We have that dot. This one should be equal to 1. And remember, this one is what you call, look at this here. It should give you what you call the multiplicative inverse, multiplicative identity. You see? So this one should give you the multiplicative identity. But now the problem is in here. But a half is not a natural number. This one is not a natural number. Meaning, therefore, that the set of integers equipped, the set of natural numbers equipped with multiplication does not satisfy this property 4, because its inverses are not natural numbers. The inverses of its members, except only 1. The inverse of 1 is 1. But all these others, the inverses are not natural numbers. Are you saying that? Yes, that is it. So look at this. Just to, so instead of writing all this, don't write, if you, just in case you come across such a definition, you talk about the existence of inverse element, simply say for every element A in G, there exists an inverse. Yes, you may call this, but many times so either that or this one, A inverse raised to the power negative 1. This one is normally very popular. And now, cite that. Then you simply say cite that. Look at this. You say cite that. Just in case, like that. A multiplied by A. No. Of course, the binary operation, we don't know that is why using asterisk. No. Excuse me. It shouldn't be E there. It should be A inverse, which is equal to A inverse multiplied. No. That this one should be equal to E. This one is the general, you see, identity element. We call it E. The inverse is either this or A prime. So you have a group At any given time, if you define a group, it is an empty set. It should not be empty. Under binary operation star, that satisfies the following properties: closure property, associative property, existence of the identity element, and the existence of the inverse element. And now, in that case, when you're talking about closure property, whenever you pick any two members of that set G, you subject to that operation, you're going to have another member of G. Whenever you have any three elements of G, there is associativity. It does not matter which of the first two, which ones start, whether the first two or the last two. If you subject to that, you're going to have the same existence of the identity. An identity, an element in G is called an identity. If you subject the operation to every element, even up to including itself, you realize that you're going to have the same element. You see? So this one is the identity. It fixes every member of G. And you can have given you the alternative, the existence of the inverse. The inverse is spec'd on, that is the identity. And you notice that the inverse of every element of G is that which, when you subjected that operation to the original member A, you're going to have the identity. Now you're told that existence of identity element in G3 and existence of inverse of an element in G4 occur as a left identity in G. Anyway, those ones concerning left and inverse, don't bother yourself so much when it comes to that. That should not bother you. At this stage, that is not necessary. So all this case of not, that is not very necessary. But now, the group G with a binary operation is denoted that. I think that is something that we've seen. And if it is a plus, if the you see, if it is a binary, if the binary operation in that case, you see this one is a general, could be multiplication or addition or any other. If it is a plus, then we call it an additive group. And if it is a multiplication, we call it a multiplicative group, right? Now, the case of abelian, when you may be asked to tell when a group is said to be abelian. Of course, a group must satisfy the four properties. But if it satisfies another property, and this property is this, what we call commutativity, you can see this. It does not matter which element start. A operation, binary operation, asterisk B is no different from, you see. Bringing me to this, just to ask, is the set of natural numbers, you see, equipped with addition, is it an abelian group? In terms of plus, it is not a group. Now, in terms of multiplication, it is not also a group. You see, the set of natural numbers equipped with plus is not a group. Why? Because there is no identity element. It is not a multiplicative group. The identity element should be 0, but now 0 is not in the set of natural numbers. With respect to multiplication, the set of natural numbers equipped with multiplication does not have, every member of the set of natural numbers does not have, you see, it doesn't have an inverse, because the inverse must be inside the set of natural numbers. The inverse of 2, for example, is a half, which is not a natural number. So the set of natural numbers, whether equipped with plus or equipped with multiplication, it's not a group. It is an algebraic structure, yes, but it can only be a group if it satisfies these four properties. The set of integers equipped with, I think that I mentioned this, the set of integers equipped with, I see that. I think we talked about it. It's here, right? Yeah. The set of integers equipped with plus is a group, because whenever you add any two integers, you will have another integer. That is closure property. Whenever you pick any three integers, whether you start with the first two, then add to that, or add these ones, add that, you'll always have one and the same answer. The additive identity is 0. The additive inverse of -1 is 1. The additive inverse of -2 is 2, because when you have -2 plus 2 is 0, which is the additive identity. The additive inverse of 3 is -3, and so on. So you notice that the three properties are satisfied, and therefore there is a group. But now the question is, Is it an abelian group? The answer is yes, because -3 plus -2 is no different from -2 plus -3. It does not matter how you add integers. You will always have the same answer, whether 0 plus 1 or 1 plus 0, whichever starts. That is commutativity property. And therefore, the set of integers equipped with plus is an abelian group. So you can see that is what we mean by abelian. If it satisfies, apart from being a group, it satisfies these other properties. You can see that it's abelian or commutative. If the commutative law with respect to the operation holds in G, in particular, an additive abelian group, look at this now. The set of integers, the one that I've just talked about, integers equipped to, not really positive, the set of integers equipped to it plus this one. This one is an example of a module. And a group which is not abelian is called a non-abelian group. Now let's talk about order of a group. And we're told that, look at this, it is important that we have a clear, the number of elements it contains, you see, is actually what we call the order. We call this, that is the order of the group. If the group G equipped with this binary operation is such that G contains an element, then it is called, if it contains an element, then it is called a group, a finite group. If G is an infinite set, then we call it an infinite group. Of course, an infinite equipped with this, and it happens that it satisfies the 4 conditions, then the 4 properties, then that we call that an infinite group. Now, in this case, we have 2 examples. Another thing is that here we've talked about that there is a set of integers. Here, I would want us to see run away from that. Let's go with what it is, either Z or the other. Discuss. Yeah, is what I've mentioned. This is the is also abelian, you see, and you can see that abelian not also called a module. When we talk about this one, this is the set of non-zero rational numbers. Non-zero means all rational numbers excluding 0. Then that algebraic structure forms, you see, you can see the abelian group. The set of rational numbers are those numbers that can be expressed in the form A of a B, where A and B are integers and B is not equal to. And we see when by those non-zero rational numbers at all times, you'll always have another number. Now, you have only 3 rational numbers. It does not matter whether you multiply it at the last and then like this, the same rational. And 1 is what never that you see now for every rational number, 1 over A is also a rational number, which is also A inverse. Notice that when you have this multiplied by this, it will be multiplicative to 1. So you notice that yes, every rational number has, because 1 over A also is a set of non-zero rational numbers, and therefore all of these are satisfied. That being the case, therefore, we see that that set of rational numbers denoted by this equipped with multiplication, as mentioned here, is actually, there is a group. And when you look at, again, pick any 2 non-zero rational numbers, multiply by each other, it doesn't matter the order in which you multiply them. They'll always, it will be one and the same. A by B is no different from B. And therefore, this is also an abelian group. It is a multiplicative because of that question. And apart from being multiplicative, we see that yes, it is what we call a multiplicative. In fact, multiplicative abelian group. This one should be multiplicative, not multiplicative, not multiplication, multiplicative abelian group. Right? Here we have what we call a semigroup. We're told that this algebraic structure is said to be a semigroup. Remember, we are not saying that this one is a group. If it satisfies at least G1 and G2. So the question, look at this, G1 and G2, closure and associative. An example of a semigroup is what we call the set of natural numbers equipped with plus. At least those two. And you can see, of course, you see when you're talking about that is n, look at this. When you're talking about the set of natural numbers equipped with plus, it is true natural numbers. So closure property is satisfied. Associative also, it the second part added to the first one. You will have the same. It is associative. And because it satisfies the two, then that is a semigroup. We know very well that it doesn't satisfy the existence of another group here. Yeah, right. That semigroup is a semigroup. An algebraic structure, look at this, we have also other terms. Satisfying G1 only is what we call a groupoid. If it satisfies closure property, and if it satisfies at least the three axioms, G1, G2, and G3, then it is called a monoid. Get that? If it satisfies G1 only, is a groupoid. But if it satisfies at least the three axioms, G1, G2, G3, then it's called a monoid. These are some properties that concern groups. Of course, they are presented in the form of theorems. And this first one is that while it concerns the left identity, is also a right element. Well, ignore that. Yeah, you can have them for your own consumption, but I don't intend to take you through that. The case of uniqueness of an identity element, I think I've talked about that is that the identity element is unique. That one you can read. Yes, this one is okay. Go through that, but I would not lay a lot of emphasis on that also. The case also, the same case applies to this, the left cancellation, right cancellation, no. Those ones you just peruse through for your own knowledge, and at least to be more equipped. All these theorems, well, you see, in your cases, I would not want to engage you through a lot of theorems, and yet you see your area of concentration is more of application than pure mathematics. And so that is why you see that, well, I'm being careful in as far as taking you deep into that is concerned. Now, as to the case of subgroups here, I think this is a part that is something very small. Look at this. We have this as a group. We have these two algebraic structures. And these two form a group under the same binary operation. So what is key here is the same binary operation. So if this is plus, then this one should be a plus. If this is multiplication, this one should be multiplication. But now the catch is in this, that if S, this subset, is a subset of this, yes, each one of these is a group in its own right. But now we notice that this one is a subset of this, then we say then S is a subgroup of G. And this case of a subgroup at times is written this way. Yes. That is it. Or at times we could have this, but this one is not. We say this one is G is a supergroup of S. But this one is more popular. And we're given an example, the set of all integers under the binary operation of addition is a subgroup. Yes, the set of all integers is a subgroup of the set of rationals under addition. Because you see every integer is a rational number. And you see each one of these, the set of integers, look at this, equipped with this. And then, of course, the set of rationals, look at that, equipped with that. Each one of these is a group in its own right. You see, each one of these satisfies the four properties. But the set of integers is a subset of the set of rationals. Every integer is a rational number. Every integer can be expressed in the form A over B, where A and B are integers. And you see B in that case, when you're talking about this, B is always 1, right? And in that case, therefore, this one is a subgroup of that. But now what happens in this case is that I would not want to delve so much deep into that. Just have that brief definition of what a subgroup is, and also that example, this example also, just in case you asked to, I would not admit such a fellow at the moment. That is a joke, honestly. We are at the tail end. So we stop there in as far as subgroup is concerned. And you told a subgroup which is neither G nor E, or the identity element alone, is called a proper subgroup. Yeah, it's neither the whole group G, and neither is it the identity element, which is, of course, it is a singleton with the element E alone, is called a proper subgroup, right? That is it. So I think it will be okay if we stop there. The general properties, those ones are for your own consumption. You may read those ones, but I wouldn't wish to lay much emphasis on. This is an example of a group. This is a type of a group. We call it cyclic groups. And this one we shall introduce ourselves to in our next meeting. And this is where we shall discuss what we call, that is especially the set of, that is the group of integers modulo n. What we talked about yesterday, integers modulo n. And I think you still remember two integers are said to be congruent to each other modulo n or modulo m if the difference between the two, of course, are divided by that m. And well, let's call it a lecture up to there.